All right, welcome back to VSAT. This should be the end of your second week at class. So by now you should be fairly familiar with the equations of field capacity minus the permanent wilting point equals the available water. From there, you should be familiar with how we can reach our total PAW by taking the available water and times it by the depth of the root zone to give us total plant available water. And we also should be familiar with the management allowable depletion. Take our available water and times it by our managed allowable depletion to reach our soil moisture depletion. And if you know what our soil moisture depletion is in between irrigation cycles, we can replace that water without being wasteful. And if we're using MAD properly, we'll ensure that we're using our irrigation system most effectively and ensuring that we're not putting any undue stress on our crop and ensuring that we have optimal growth rates and yields. But there is another way to determine what a soil moisture depletion is. And this is a pretty easy equation to understand. And basically, if we know what our field capacity is, we can, using various instruments, do a test and determine what the moisture content is on any given day we do that test. And if we've already determined what our field capacity is, a couple days later, we check the soil content and we understand what the moisture content is at that point in time. We can determine what the difference between the field capacity is and the moisture content is, and that's another way we can solve for soil moisture depletion. All right, and then again, if we know what our soil moisture depletion is, we know how much water that we need to put back in. All right, so simple equation today: field capacity minus the moisture content equals the soil moisture depletion. All right, we should be comfortable with field capacity at this point. How do we determine what our moisture content is? This is if you're using devices like the one we use at Archie's Acres, which are watermarks. We're basically these gypsum blocks that we put in the ground. First we soak them in water overnight, then we put them in the ground, and as the ground dries out, it starts pulling the water out of those blocks that are in the ground. And using a meter, we can measure that pull. We can measure how much pressure is being pulled against the water out of that block. And we can track that and we can establish what our moisture content is, and then that helps us determine how much moisture has been depleted. So for instance, by using devices, we can calculate that our field capacity is 3 inches per foot. If we use some form of device, we irrigate one day, we fill up a reservoir, now we're at 3 inches per foot. Let's say a couple of days later, we go back, we measure how much moisture in the ground. We determine that in the ground, there's 2 inches per foot of moisture that's left. Well, if we take the field capacity, which is 3 inches per foot, subtract the 2 inches per foot of water that's left in the ground at that time, we can then determine that there's a total amount of soil moisture depletion of 1 inch. And if we need to, if that's the day we're going to irrigate, now we know how much water we need to put back in. We need to put 1 inch of water back in again. So this helps us be more effective in using our irrigation systems and ensure we're not wasting water and provide optimal plant performance. So just a quick example here, field capacity is equal to 28% and our moisture content is equal to 23%. And we want to solve for our soil moisture depletion. Again, field capacity minus moisture content equals soil moisture depletion. Just plug my numbers in here: 28% minus the 23% equals 5%. I can then convert that in inches per foot, because 5%, which SMD is equal to, 5% is equal to 0.05. I could times that by 12, and that gives me a soil moisture depletion of 0.6 inches per foot. All right. And now I know when I irrigate, if I'm irrigating today, I know I need to put back in 0.6 inches of water in that given time. All right. So that one's pretty easy. But now we're going to talk about water penetration. All right. It's a little bit more complicated. One of the things we need to know in order to understand how water penetrates the soil is we need to understand how much moisture has been depleted from the soil. All right? More moisture that's been depleted from the soils means your water is going to move less deeper in the soil, if that makes sense, right? Because if the soil on the top is super dry, it's going to absorb most of that water that you apply, preventing it from moving deeper into the soil profile. And if the soil is wetter, it will allow that water to penetrate deeper, and you'll get more depth. So it all depends on the soil moisture depletion, and understanding the soil moisture depletion takes into account different soil types, right? Because there's two ways we can determine soil moisture depletion: available water times MAD equals SMD, or field capacity minus moisture content equals SMD. Knowing what the field capacity is and knowing what the available water is, either of those methods, take into account soil characteristics and the capacity of the soil. All right. So when we determine what a soil moisture depletion is, the soil characteristics and its capacity, the soil's capacity, is already taken into account. All right. So if we know what that is and we know how much water we can apply, we can then determine how deep that water is going to penetrate. Now, why is that important? Well, for one, it depends on the crop you're going to grow, but you're going to want to make sure that water is getting all the way to the depths of the root zone, again, so the plant has full access to water, nutrients, and it's not going through any undue stress, and now we're reaching maximum yields and potential. But two, again, if we need to leach salts or anything like that, we want to make sure that the water is pushing the salts below the root zone, and so we can calculate how far the water is going to push that salt down by knowing the depth of penetration of water. So the new equation we're going to teach you today is if we take the amount of applied water, what I call AA, stands for amount applied, and this is in inches, all right? We divide it by our soil moisture depletion, which is inches per foot. We can then determine what our depth of infiltration of the water is. All right, so amount of water applied in inches divided by soil moisture depletion in inches per foot gives us depth in feet. And again, in the equation process, we have inches and inches per foot. The inches cancel each other out, and we're left with feet for the depth. So an example of equation is if there is amount applied is equal to 3 acre inches, and our soil moisture depletion is equal to 0.8 inches per foot, we want to solve for our depth. All right, so now all you do, utilizing the equation, let's plug our numbers in. 3 inches of water. What's the difference between acre inches and inches? Well, on a two-dimensional level, there's no difference. All right. What 3 acre inches means is there's an acre of water covered with 3 inches of water. Or excuse me, it's acre of land covered with 3 inches of water. An acre inch is 1 acre of land covered with 1 inch of water. But when we're looking at the depth of penetration, we could care less whether it's just in inches or acre inches. All right. So we have 3 inches of water that's been applied. We divide that by the 0.8 inches per foot, which is the soil moisture depletion. And 3 divided by 0.8 inches per foot gives us a depth of 3.75 feet. Now we know how much water's been how deep the water is going to infiltrate into the ground. But first we need to know what our soil moisture depletion is. How can we determine that? Again, we have 2 different ways. Amount applied times MAD equals SMD, or field capacity minus moisture content equals SMD. But we have to start with that initial equation that we learned on day 1. Field capacity minus permanent wilting point equals the available water. That equation alone helps us reach all these other equations, helps us understand the characteristics of soil and their capacities, and helps us branch out and to utilize our irrigation systems the most efficiently and provide the best yield. So here's a second example. How much rain will it take to penetrate 3 inches. So in this case, we know what our depth is. All right, we know what our depth is. It's 3 feet, excuse me. 3 feet. And our soil moisture depletion at the time was 0.5 inches per foot. All right, so we don't know how much water we applied, but we know, and went 3 feet down, we know before it was applied, we're at soil moisture depletion of 0.5 inches per foot. So I don't know what my amount applied is, but we know if we divided it by 0.5 inches per foot, then it came out to a depth of 3 feet. Now what do I do from here? I want the available water to equal something, right? I want the available water to stand alone on this side of the equal sign. So how do I get rid of this 0.5 inches per foot? Well, it's asking us to divide the available water by that 0.5. So I can get rid of the 0.5 by doing the opposite, by timesing it. But whatever I do this side, I then have to do the other side, all right? So it looks like this. We're going to multiply a side by that 0.5 inches of water, inches per foot. Now, excuse me, that's 0.05. Now it's important to know when you take 0.5 and multiply it by a dividing 0.5, it really comes out to a 1. All right, it doesn't actually cancel out. It comes out to a 1. So we're going to have 1 here, but it's going to be amount applied divided by 1, and it's going to equal whatever. All right. Let's just stop right there, actually. I don't think that made any sense. So I'm just gonna start from where we're at here. All right, is that cool? Well, yeah, Rob will edit it out, or whoever. All right. So we know our depth is 3 feet, and we know our soil moisture depletion is 0.5 inches per foot. So I'm going to utilize the equation. Again, I don't know what my available water is, but I know if I divide it by 0.5 inches per foot, that it equals a depth of 3 feet. All right. Now I want this available water amount applied to stand alone on this side of the equation sign, right? So I got to somehow get rid of this 0.5 inches per foot. So I got to do the opposite of what it's asking me to do. So if I have available water divided by 0.5, I can get rid of this 0.5 by multiplying, again, doing the opposite is what it's asking us to do here, by multiplying it by 0.5. But whatever I do to this side, I then have to do to this side. All right, so multiply that by 0.5. That means our available water is going to equal to 3 feet times 0.5. Again, this is inches per foot. And what happens when we have 3 feet times 0.5 inches per foot? The feet will cancel each other out, and we're going to be left with 1.5 inches. But again, all these equations we learned this week starts with field capacity and understanding what the permanent wilting point is and driving available water. All right. So that concludes the math for the second week. We'll see you next week.